Okay, hey guys. Alright, so this is the second part of Chapter 5. Yesterday, you looked at the history. How did we get the periodic chart, the way that it is? And here we're going to be looking at the periodic trends. What is exactly a periodic trend? Well, if we take about trends in cars, for example, we know a trend is a predictable change in a certain direction. So, for example, here we can look at cars. We can look at the Mustang from '64 all the way through 2014. And you may notice that there's a general change in the direction for this. And the pretty obvious one is, if you look at the box shape of the '64 and compare it to the 2014, the 2014 is now more well-rounded. Well, why? Well, aerodynamic styling, cut down on air drag, friction with the air, and improving gas mileage, which means less money out of your pocket for gas. But that would be an example of a trend in the real world. We can talk about trends in clothing. We can talk about trends in shoes, for example. We can even talk about trends in movies, because 10 years ago we weren't seeing all these superhero-themed movies coming out. No, we've been seeing that in the last few years with the Batman, Captain America, the Avengers, all those. So that would either be an example of a trend in the real world. Okay, let's take a look at chemistry here. We got to talk about the first trend. We got to look at atomic radius. Well, what do we mean by atomic radius? The size of the atom. Okay. Now, we measure it using X-ray diffraction. So we shoot X-rays through a bunch of these atoms, and we kind of get the idea about the size because we can look at the electron cloud. Remember, the electron cloud is like the Ontario Mills, where we have, say, Peyton and Leah, for example, that they're inside Ontario Mills and they can go anywhere they want, and with Heisenberg we don't know where they're going to be, but they have unlimited spending. Okay? Yes, I chose Leah and Peyton. Okay, for the other classes, chillax, it's not the end of the world. Okay, it's just coming into my mind because I don't know if I'm going to be here today or not. Okay? Depends on how my dad is doing. So, then generally speaking, the trend, the radii, there is no such word as radiuses, okay? It actually gets smaller if you're going from the left to the right across a period, a row of the periodic table. So in other words, if we think about it, okay, if I am going to start on your left here, okay, and here I am this big, there we go. Here I am. Big. Okay. Big radius. Now, big. I'm starting. And then as I go across the row, I'm getting smaller and smaller and smaller. Okay? That is the trend. The atom is going to get smaller as we're going from the left to the right. As we go from the top to the bottom of a group, a column on the periodic chart, the atom tends to go decrease, gets to be increased from small as it's going down, it's getting large. Okay? So that's the idea. So if we look at it here, that's our general trend, atomic radii. It gets bigger as you're going down, it gets smaller if you're going this way, which means if you're going from right to left, going to get bigger. And if you've ever seen Christmas Story, think about the character that had all the layers of clothes on him to keep himself warm. Okay? Think about that. The more layers of clothes he has, the bigger he gets. The more layers of electrons atoms have, the bigger they get. And that's what we see here for ionic radius. Okay, cation ions are smaller than their parent atoms, and anions are larger than their neutral atoms. Okay, wait, Canu, I don't remember the cation-anion thing. What's up with that? Okay, atoms can be in one of three categories. They can be neutral, no charge. They could be positive, or they could be negative. Okay? All that is determined by how many electrons that they have totally. Okay? So, a cation would be an atom that has lost electrons. Remember? The cation. The cat, scratch, scratch. Notice the positive sign I'm making with the cation. Like that. The anion gets bigger in size. Why? Because it's picking up electrons. That's why. Okay? So I got a couple of examples here of sodium losing the electron. Notice how it shrinks. Here's fluorine picking up an electron. Look how much bigger it gets. If we go and look at this, here's a chart of ionic radius. Here's sodium with its regular number of electrons, loses an electron, and now +1, but look how tiny it is. We can go to chlorine over here. Here's chlorine with its 7 electrons. The moment it picks up that 1 electron, look how much bigger it gets as a result. That's the idea. Okay? So, lose electrons, atom gets smaller. Pick up electrons, atoms get bigger. Atom stays the same, atom stays the same. Those are the 3 ideas. So, lose electrons, atoms get smaller. Pick up electrons, atoms get bigger. That's just the way it is. Ionization energy. This is another trend, and it is a biggie. Because how much energy do we need to rip that electron out? Yeah, exactly. Rip it out. I need just tear it apart. Come on, you little punk. Give me that electron. No, I'm not going to give it to you. I'm taking it. Boom. And that's it. How much energy does it take? So here's an example. Lithium plus energy, and we get lithium plus and the electron. Okay? That's called the first ionization energy. If you go from the left to the right, the ionization energy actually goes up. It's harder. You need more energy to go and rip out electrons from the right side of the periodic table compared to the left. If you're going from top to bottom, well, that actually gets easier. The ionization energy is less. Why? Well, because you got so many electrons, like, I don't really care. Yeah. So ionization energy, this is it. If you're going from the left to the right, it's harder. It's harder to go and rip an electron out of chlorine than it is out of hydrogen. It just is. And if we're talking about going from hydrogen down to francium, well, francium, like, that's not a big deal to go and take an electron from francium. Bigger deal if you're trying to take it from the hydrogen. Definitely. Well, how come? Well, that's because the electron in the hydrogen is the closest to the nucleus. Yes. Okay? Okay. Let's talk about electron affinity. How much energy is needed to add an electron to a neutral atom to make it negative? How much electricity? How much energy is needed to add an electron to a neutral atom to form a negative ion? In other words, to make it an anion. It is the absolute opposite of ionization energy. It increases from left to right, okay, along a period. Okay, that's pretty much it for electron affinity. Now, electronegativity. How much attraction is there between the nucleus and the valence electrons? That'd be a biggie. Electronegativity. How much attraction is there between the nucleus and the valence electrons? Typically, we use that for atoms bonded in molecules. Now, Linus Pauling came up with this, and the noble gases, with the exception of krypton and xenon, there is no electronegativity that we can measure because they're noble gases? Yeah, okay. We'll go with that. So, what's up with that? Well, if we think about it, we can look at lithium and sodium and potassium, these guys here, and they typically have 1 electron to give away. So, you know, the attraction between the nucleus and the valence electrons, it's, yeah, not a really big deal. In fact, it's more like, okay, fine, we lose it, so what? Okay, now, when we go up on this side here, we look at fluorine, chlorine, and oxygen. It's like, oh yeah, I want my electron. I want it badly, and I will do anything to get it! Yeah, I want that electron. So, electronegativity is definitely going to be higher on this end here compared to on this end here, where they're saying like, yeah, okay, you can have it. Here it's like, oh baby, give me that electron, man. I want it, and I want it now. Just like our society today. Instant gratification. Okay. So, at this point, guys, let me see how much time I got left. Oh, yeah, I'm doing good. All right. I'm looking at and seeing how far can I go. Whoa. All right. So we looked at trends. We looked at the idea of what happens with the atoms and how they behave. Why did they behave the way that they do? Okay? And you're still going to mess around probably with the periodics too, as well. Okay? So, I'm going to go a little bit further. I'm going to talk about a few families, and then we're going to go from there. So, 5C, element families and their properties. So, we're looking at the study of these elements and the compounds that they form. So, let's look at hydrogen. Hydrogen is its own thing, really, even though it is on group number 1, and it's on the very top. If we were to go and look at our hydrogen, we'll notice, hey, it's right up here at the top. Okay? It is its own beast. Now, we tend to think about beast being huge, but hydrogen's its own beast because it can influence many, many, many things. So, now Henry Cavendish was the guy who discovered it. Physical properties, well, it's a nonmetal. It's odorless, colorless, and doesn't have a taste as a gas. Typically, it's not found by itself in nature. That's because it can be taken by other things in the process. From going from a gas to a liquid, it's negative 253 Celsius. Oh my gosh, it's cold. Ah! It doesn't conduct electricity. Say, well, how come? Because it typically loses its electrons. It can't do anything. That's why. Oh, this is a nebula. It is a star factory in the nighttime sky. All that pink that you see there in outer space, it's hydrogen gas. And how do we know it's hydrogen gas? That fingerprint of light, that spectrum. Yeah, it's really awesome. Oh, look! Pink gas again! Right, because we got electricity going through, we got energy going in, and it's causing the electrons in the hydrogen atom to go whee! And then they come down and they give off that pink light. Yeah. Now, similarities, it's really reactive. Oh my gosh. It does combine with lots of elements. Okay, you find hydrogen in so many things. Oh, from soccer balls to charcoal to lipstick to Kool-Aid to pencils, pens, cell phones, your dog, your cat, your mom. Yeah. Commercial sources, atmosphere and electrolysis. Electrolysis, we use electricity and break apart the water into hydrogen and oxygen. Oh yeah. Oh yeah. Uses, well, we use hydrogen in ammonia production. Ammonia is NH3. We can use that for many, many things. Okay? So, do I want to go on with that? Yeah, I'll move on. I'm going to talk to you guys about group 1 alkali metals, okay? Chemically, they're very reactive. They have physical properties, okay? And this is the group 1 metals right here: lithium, sodium, potassium, rubidium, cesium, and francium. Okay, they have 1 electron in their outermost shell. They are so reactive. They're metallic and they're soft. Meaning that it's kind of like working with clay, but I wouldn't touch that. Because it will react. It will react with the air. It will react with the perspiration that are in your fingertips, and it will blow your hand off. So, you know what? Don't be stupid, okay? Because there were people who made that mistake in the past. None that I personally know of. Okay? What else do we know? Well, they react really readily with water. They lose an electron very easily. Oh, that's a biggie. Uses: street lamps, glass, explosives, fireworks, soap, paper. Oh my gosh, this is not hydrogen, folks. This is the sodium, the lithium, the potassium, the rubidium, the cesium, and the francium. We use those things. Explosives. Yeah, I can buy that one. Absolutely. Okay, and with that, I'm going to stop here. So we talked about periodic trends, and we also got into group 1 a little bit, the group 1 elements, how reactive they are. Signing off.